Good afternoon, everybody. I think you've been through quite a few presentations, so hopefully I'll get a topic that keeps everyone awake and keeps energized. Oops, sorry. So what I'm going to talk to you about today is about a study that Solvay completed about how a composite intensive design could bring value in battery enclosure. Battery enclosures are everywhere, and there's many examples here today. And what we wanted to do was to actually find out within Solvay, everyone talks about lightweighting, about the value of composites, but we wanted to go beyond lightweighting. We wanted to understand, more value that we can bring to a customer rather than just lightweighting. So this is what this presentation is about. It's the first phase of a conceptual sort of design. We have moved on to the second phase, which isn't completed yet, but will soon be completed. So if there are any more interest, then you can see me at the Solvay stand, or at the end of this presentation, we can ask some questions if there's time. First of all, I'd like to first introduce Solvay. If you don't know who Solvay are, there's a booth here, M41. We're a medium-sized global company, and we're heavily invested in advanced materials and chemical solutions, working heavily around sustainability to meet the future demands of our key markets. One of the key differentiators we feel about Solvay is just our pure breadth of materials that we offer. So not only is it just the injection molding materials, which are here on the left-hand side, which are the high-performance aromatic materials, but we also have fluoropolymers, which are used for high-performance sealing applications. Also, the fluoropolymers are used extensively in battery technology today. Solvay are one of the leading suppliers of fluoro solutions into battery cell sort of chemistry. We then move into more of the composite, which we'll focus on today, both thermoset and thermoplastic. But also we have solutions covering adhesives, and also we make our own carbon fiber sort of technology as well. One of the most important aspects of this particular project is our approach from an application engineering perspective. So we start really right at the very start when we're talking about a concept, and we can support developments, conversations with customers all the way through to the final actual solution. This particular presentation today will focus on more the early part, the understanding the customer needs, coming up with a solution that we believe will bring value. Just to give you some insight, the second phase of the project, which will be completed relatively soon, we'll be looking more into the center of this particular chart. We'll be doing some more of the trade study analysis and more of that deep application development. So again, that's further work that Solvay are working on, but this is our application development approach. To actually do this work on battery enclosures, Solvay are experts in materials. We're not actually the experts in battery enclosures. Yes, we know a certain amount about battery enclosures and their technical requirements, but to really get deep into the technical content and really start understanding the current pain points of customers, we had to work with somebody. We did screen a number of different companies that we could work with, but in the end, we actually worked with Ricardo on this project. Again, they're a well-known automotive design and engineering consultancy. They have the expertise in battery technology, not just in cells, but all the way through to battery enclosures as well. So this particular project, Solvay worked with Ricardo. So Solvay were bringing the material knowledge, and Ricardo were bringing that background to the application performance and also the current pain points that they saw on the market from their customers. So the one thing that I've already highlighted is we wanted to talk about this subject and talk about composite materials and not just focus about lightweighting. Very often we see in the press that the composite materials are often presented as their value proposition just about lightweighting. So we wanted to take a step back. We wanted to look at the solution more at a holistic level. So we didn't want to just look at designing individual components. We wanted to look at finding out what the real issues were today, and then we could build almost like a mission statement around the project moving forward. So the mission statement is important to generate because it provides focus for all of the work that we did in developing designs and using all the advantages of composite materials to solve pain points of some of the incumbent metallic materials. So what we have done is teaming up with Ricardo, that allowed us to have a very strong base. So the baseline is what is called the Ricardo FUVA battery pack. So FUVA, F-U-V-A, stands for Future Vehicle Architecture. So Ricardo do a lot of work directly with OEMs, and that work is obviously confidential. So what Ricardo have actually done is they've developed their own electric vehicle that they can use to promote their own services and their own expertise. So with working with Ricardo, they gave us access to their incumbent metal battery pack enclosure that is used on the FUVA vehicle. When we start talking about our solution, we believe that we will be focusing more on the high performance or premium market segment, where we're looking at sort of low to medium sort of volume initially. We started off by really trying to understand what this part has to do, what are all its functionalities, and also what are the current pain points. Then that would really allow us to start thinking about how this design could look like in a composite intensive design to start bringing some customer value. So right at the end of once we have the design and we've been through this process, this mission statement, we are going to validate the performance again in a virtual engineering environment, but we're going to validate it against some of what we see are the key mechanical performances, the China crush, the modal stiffness, and some of the abuse sort of shock cases. And at the end, what we will have is a direct comparison to the incumbent steel design and the composite sort of design. So you see a little bit of information there around what the FUVA battery pack is. It's what we believe is a larger SUV sort of style battery pack. It actually has 36 modules, which you'll see as the blue boxes. In each of these modules, there are 12 pouch cells. Again, we know on the market there is lots of variation between pouch, prismatic, cylindrical cells. There is cell-to-pack scenarios. It's impossible to cover all of it, so you have to base it on something, and this was our baseline. So it's a battery pack with a power of 94 kilowatt hours. Important here is that the steel enclosure is 141 kilograms in weight. The dimension of the pack is quite a big pack, and it's a traditional water glycol sort of cooling. So this is really the scope of the project, and this is what I'll be talking about for about the next 10 minutes or so, and therefore hopefully just leave a little bit of time for questions. So before, as I said, you can really start understanding on how to design your battery pack, you really have to understand what are the key functionalities of what a battery enclosure has to do. And someone in Solvay told me that it's just a box, Mark, but it's quite a complex box, and you have to understand what it really has to do. So this is where the benefit of working with someone like Ricardo really helped us, that we spent a significant amount of time just really understanding all of these sort of functionalities, and we really understand that they're very much interconnected with each other. So what we did with Ricardo, based on the FUVA vehicle, we did a Pew analysis, and based on their experience, we came up with a list of functionalities that we could put as a priority. So number one is obviously safety and crash. That is something that is a pain point for customers. That's what keeps the customers awake. The fire, the burn, the EMI, the structural performance. This is something that you have to comply with. So this was something that was almost like given. You have to comply with the safety and the crash. But then we did other analyses and realized that quite high up, with talking with Ricardo, they were saying that the actual volumetric efficiency, so the space within the pack, is also really important. And then we go down the list, and what was important in this is that lightweighting came out towards the bottom of how important it was. Yes, it's still important, but if you want to have a composite design, you need to have something else other than just lightweighting. You need to be able to communicate on other things just than lightweighting. So we sort of started with the problem before started working on the solution. And one thing that's missing off here that is a given is also sustainability. So the recycling, all those aspects. So that is something that we recognize. And again, with our broad portfolio of materials, the thermoplastic composites that we're developing is obviously something that will fit within that sustainability story. We're doing a lot of work on thermosets as well, which will allow those solutions to be recycled as well. So sustainability is at the forefront of our mind when we talk about materials. When we talk about technical, we really focused in and zeroed in on that number two, that package, the volumetric efficiency. This is where we thought that the design flexibility and part integration potential of our materials could really bring a solution. Also, we can reduce the number of sealing surfaces that we observe within the metallic pack. And of course, the lightweighting is sort of given because we're looking at a composite solution. So this is our battery pack. We've tried to make it as holistic and agnostic as possible. So we haven't touched the power distribution unit of the FUVA pack. We haven't touched the module layer. We haven't touched the cooling system. But interestingly enough, when we looked at the cooling system, we realized that there was a tremendous amount of benefit in our materials and how it could make the cooling system more efficient as well. But that was outside the scope of this project, so we didn't touch on those middle three. We focused on the cover and we focused on the tray. And what we realized is that a lot of incumbent solutions have a very structural base, and the lid is just a lid. It doesn't really take part in very much sort of structural part of the mechanical performance. So here, what we can do is we can integrate some more functionality into the top cover, so that can actually contribute more to the structural behavior. So what we can do with our thermoplastic technology, we can integrate cross members into the top cover. We can integrate cross members into the bottom cover. Once you're integrating those features, you can actually introduce things like module retention features that are actually involved in those cross members, and therefore you're eliminating a number of other metallic, bolts and other structures that you can actually sort of eliminate. So there's a huge amount of benefit in this integration sort of approach. What we've also got is a very important perimeter frame design, which is allowing us to meet crush sort of performance. Haven't really gone into too much detail here, but this is something that's very important to the mechanical performance of the actual battery pack. So how have we gone about, if we just focused on that volumetric efficiency, how have we achieved that improvement in space that we see in the pack? So the actual packaging volume, where this battery pack has to integrate into the body in white structure, stays the same. What we're trying to do is we're trying to get more space, which was seen as that key pain point. So you look at the perimeter crush frame, you see that in the incumbent metallic design, there's around about 120 millimeters taken up by the actual perimeter frame. In the design that Solvay have developed with Ricardo, we've actually reduced that sort of down to just under 85. So when you look at benefiting that amount of volume all the way around the pack, that starts to become something that's significant. what we also observed in the metallic pack was there are quite a lot of cross members that were involved in achieving that mechanical performance. And each of those, both longitudinal and lateral cross members, take up space. So every single one takes up almost 25 millimeters of space, which means that space that can't be taken up by cells, which are the most important part of a battery enclosure. So with a more integrated design approach, you can still get the structural performance, but you can actually save a lot of space just within that composite sort of design. And also, depending on your module size, you can integrate a lot of module retention features in these cross members as well. Also, it's not just the crush frame, it's not just internal, it's also the actual Z height. So Z height can be very important in some vehicles, particularly because the passengers sit above the battery pack. So I think this is important. It's not maybe a tangible value, but if you can create more space for rear seat passengers, really see this as a benefit. That came out in some discussions. So what we can see actually is in the metallic design, the power distribution unit is almost very much sitting very proud on top of the metallic pack. What we've been able to do is actually bring that power distribution unit more internal, so it's still protruding at the top, but it's a significant reduction in height. And then the overall height of the other part of the battery, with our design, we've been able to minimize the lid and the base. So again, you start to get some improvement in that overall dimension. So you start combining those overall dimensions together, you start to get an idea of what that space can be. If you understand what that space is, you can start designing modules and cells to take advantage of it. Once we had the design, Ricardo did obviously the simulated load cases. So the main one we were looking at was the China crush. I know there's been an updated China crush since, or a Chinese standard 2020 standard, which is important to talk about in the second phase, because that's bringing in new regulations for thermal runaway. But here, the main part here is to make sure the battery pack at any location around the outside, the exterior, we can meet the 100 kilonewton sort of load case. So we tested 5 locations around the pack, some of them in line with the cross members, some not, and we all met with the 100 kilonewton. We have actually spoken to some customers, and they've said, well, yes, the 100 kilonewton is achieved, but normally we would want to have a little bit more safety margin on that. So that's another reason why we're going back into a second phase, to actually improve on the safety margin of this China crush. The other aspects, we needed to meet the modal stiffness performance within the vehicle from modes 1 to 21. That was all successfully completed. We did a 25G abuse shock, and also did underfloor jacking performance as well. So as this was a proof of concept sort of performance, these were the key mechanical performances that we wanted to perform, just as a look and see, to see, okay, we've got some potential benefits in volumetric efficiency, but does it really have the potential to meet the performance that this battery pack has to meet? And here again, there is some positive indications that this is a battery enclosure that has potential legs to bring some customer value. So when we put a side-by-side comparison, the actual the key standout is the volumetric density, which is the watt-hour per litre. The metallic design, the steel design, had a 220 watt-hour per litre, but with the space that we developed and putting cells in all that space, we've been able to increase that to about 270. We've actually, the volume of the enclosure, so this is the volume taken up by the material, is significantly lower as well. Even without using lightweighting as a driver, we have reduced the weight by about 75 kilos. So even though lightweighting is not important, 75 kilos is still something that's significant. And we're producing a lower number of structural parts, and obviously that Z height has been improved as well. So there's a lot of other work going on. I'm just conscious of time. So this is what I'm talking to you about is the conceptual design. There's lots of other work going on at Solvay right now. We're doing huge amounts of work on material testing for thermal runaway and fire, really answering the current industry's sort of requirements. We're doing a lot of work on thermal runaway and significant amount of work on our materials for shielding as well, because all these are important to answer that safety sort of question. So moving forward, as I mentioned, we're in the second phase of the project, which should be completed very soon. So we're really going to be finalizing our material characterization for fire protection, thermal runaway and EMI shielding. We're going to go further on the mechanical. We've got potentially very positive results in the first phase, but we need to go further. We need to start understanding how this solution performs in vehicle crash. We want to mature the design, and we want to go further in that simulation around thermal management. And of course, we're very much open to having more customer engagement as well. So this is just my final slide. At the start of this project, we wanted to talk about composite design and not just talk just about lightweighting. So we think it's more than part integration. It's more than achieving these complex geometries. It's more than having that environmental resistance to the end environment. It's more than having reduced tooling costs and reduced number of toolings. What we've uncovered is that we believe there's a significant improvement in that volumetric efficiency that can be achieved within a composite battery pack. So we're not so naive to think that this is a design that can go everywhere sort of straight away. I think we're talking about a high-performance battery pack. We're talking about it being used in a UAM environment where lightweighting is significantly more important, but also in this premium luxury sector of automotive as well. So with that, I'll finish the presentation. If you want to contact me, there's my email address. I'm here today. I'm here tomorrow. So the Solvay stand is M41. So if you wanted to come and have a discussion with me about this part of the project or the second phase of the project, which is already ongoing, more than willing to have a discussion with you. So with that, then, if there are any questions, more than willing to have take questions from the audience in the small amount of time that we've got left. So when you start talking about, the steel designs are where you've got these really high volume, sort of manufacturing. So this is why we focus a little bit more on something that's at a lower, sort of platform size, because then those mass, steel, type production methodology isn't really our direct, sort of competitor. But when we have done some baselining, and the material cost isn't that far away at this conceptual stage. So that's why the second phase of the project is really when we get to a final design. This is a proof of concept. We get to a final design. That's what we're going to look into: tooling cost, parts, manufacturing costs, assembly, capex, rate. Those are the key questions. So we believe we're in the right area. If it was way off, we would need to stop. We would not. But there are some key questions that we still need to answer to have those meaningful discussions with customers, and that's what we're really trying to focus on in the second phase. But very, very important question. Okay. Thank you.